Hello and welcome to the on-air session towards the discovery of other Earths, the role of AI. Hello and welcome to the on-air session towards the discovery. I'm so sorry. We have today Yann Alibert and Sara Marques from the Bern Space Research here about a super exciting topic. I'm really excited about the next 45 to 60 minutes. You have the chance to ask questions in the chat. We'll have a Q&A session after the session. This is the event is part of the Swiss AI Weeks, organized by the Swiss AI Weeks and Wildcard Media. And now I'm just handing over to Yann and Sara, and I'm excited to hear what's coming.
Hello, thank you for the introduction and welcome everybody to this session. So I am Yann Alibert. I'm professor at the University of Bern in space research.
Well, I am Sara and I'm a PhD student with Yann Alibert, and we are working on how to discover other Earths with AI.
Okay, so as it was said, you can ask a question during the talk in the chat, and then at the end we'll have 20 minutes to answer in more detail to these questions. Also, during this session, we will ask you to answer some kind of quiz, and so then you will have a chance to answer the quiz in the chat. So I will start now, and so as it was said before, this is what we will address today. I will start by explaining what is planet formation very rapidly, and then we will have a look on exoplanets, so planets outside the solar system. And then I will hand over to Sara, who will explain what is the architecture of planetary systems and how we can study this using AI and generative models. And then we will give some example at the end about real observations. So to start with, planet formation in a nutshell. So planet formation starts actually after star formation. So to understand planet formation, we first need to have an understanding on star formation. So what we know is that stars are born in giant molecular clouds. You have here some images of what is called as the pillars of creation. So this is a very huge giant molecular cloud. That was observed first with Hubble on the left and then with James Webb Space Telescope on the right. So what is a giant molecular cloud? This is a very big cloud of gas, cold gas, and cold gas which is very cold and very, very large. To give an order of the idea, so the size of clouds are light years or hundreds of thousands of astronomical units. So what is a light year? A light year is the distance that the light will travel during 1 year. And this is around 10,000 billions of kilometers. So it's huge, huge distance. An astronomical unit, or AU, is the distance between that you have between the Sun and the Earth. And it's 150 millions of kilometers. So it's already quite big distance. Also, to give some order of magnitude, the size of the solar system, or the orbit of the outermost planet, which is Neptune, is 30 astronomical units. So you see that these molecular clouds are much, much, much bigger than the solar system itself. So now, in these molecular clouds, you have gravitational forces. So there is gravity between different parts of the cloud. And when the cloud starts to be big enough, then it will collapse because of gravity. And this collapse will form stars that you see on the left image, for example, where you have dark places and then you have tiny little red spots. And these red spots are stars that are forming just when we see them. Now, when you have a star that is formed, at the same time, there is something very interesting that happens. You have formation of a disk that is around the star. So you have here some very nice images of disks that are called circumstellar, like around the Sun, or protoplanetary, that means that will form planets. So these protoplanetary disks They are much smaller than the clouds, and again, to give another of magnitude, they have a size that is typically of 100 astronomical units. So again, as I said before, 100 astronomical units means this is 3 times the distance between the Sun and Neptune. So this is typically the size of the solar system. Also, because it's quite difficult to capture what are really these distances, the object that was launched by the Earth by humans, which is Voyager 1, that's the object that is at the largest distance from us, and it is 170 astronomical units. Okay, so it's beyond Neptune, it's quite far, but it's nothing compared to the distance between 2 stars, which is in light years. So now these protoplanetary disks, they are made of a lot of gas, hydrogen and helium, and a little bit of other things, which what we call metals or solids. So you have 1% of the mass, which is solid, and 99% of the mass, which is in gas. And to compare what is the mass of a disk to the mass of the Sun, they have a mass that is typically a few percent of the mass of the Sun. So now, in this disk, we know that dust that is 1% of the mass will collide, and then it will collide to form bigger objects that we call pebbles. Then these pebbles will form what is called planetesimals. So these are bigger objects. And then at the end, these planetesimals, by collisions, will form what is called planetary embryos. So again, to give another of magnitude of the sizes, dust, we know it's micrometer to millimeter. Pebbles are more centimeter in size, so this size. Planetesimals are hundreds of meters to hundreds of kilometers in size. So they look like, I would say, asteroids that we know in the solar system. And then planetary embryos are much bigger, like thousands of kilometers. So when we have a planetary embryo, which is big enough, again, because of gravity, it will start to attract more and more solids. And then by collisions, it will grow and grow. And then we can have 2 or 3 pathways for forming of a planet. Either we have a planetary embryo that grows very, very massive, I would say around 10 times the mass of the Earth. Then this embryo can, again, because of gravity, attract a lot of gas, and that will form something like Jupiter, which is called a gas giant. When there is a very, very little amount of gas that is attracted because the planet stays small like the Earth, then there is very, very little attraction of gas, and you end up with a planet which is like the Earth, very tiny atmosphere. And then in between, you can form something that is like Neptune or Uranus, so what is called an ice giant. So this is for the general understanding of how we form and we believe planets and planetary systems are formed. Now, for a very long time, we had only the solar system, but then we know since 30 years from now, actually, that there are other planets outside the solar system, and they are called exoplanets. So how do we know that there are exoplanets? So I will spend a little bit of time to explain how we can find and study planetary exoplanets or extrasolar planets. And there are basically 3 methods that are used. The first one is the transit method that you see on the left. So in this case, it's very simple. You have a star here, and then we are sitting at this place, and then there is a planet that goes in front of, okay? And then because the planet goes in front of the star, then there is like a shadow, and then we see a decrease of the light from the star. So what you see here on this graph, where you have, as a function of time, the decrease of the luminosity because there is a planet that goes in front of. Then the second method is called the radial velocity method or Doppler effect. So you probably all know what is the Doppler effect. That's the change of sound that you hear where you have so the firemen, for example, that come from far close to you, and then they go away. And then you hear at this point, you hear a change in the sound, okay? It's going up, more to the higher frequencies than down. There is exactly the same effect that happens with light. If you have light a source of light that is going from far towards you, and then again in the other direction. Then when it goes to our view, it will be a little bit bluer. And then when it goes away from you, it will be a little bit redder. So now if you imagine that, again, we have a star here, and then we are sitting here, and then there's a planet that orbits. Maybe it will not transit, but because of a gravitational interaction between the planet and the star, then actually it's not the planet that rotates around the star, it's that they both rotate around what is called the center of mass. So it means that when you have a star and then you have a planet, then you will have, the star will move a little bit towards us and away from us. And when we look at the color of the star, then the star will be a little bit bluer and then redder and bluer and so on. And then by measuring this change of the color of the star as a function of time, we can know what is the orbital period of a planet and what is the mass of a planet. So this is called the radial velocity effect. And this is something that was in particular used by Michel Mayor and Didier Queloz when they observed the first exoplanet around a star like the Sun. And this is what led them to win the Nobel Prize in 2019. And then the last method to observe exoplanets is called direct imaging. So direct imaging is very easy to understand. It's just to take pictures of a star. And then you have here on the right, you have here different pictures of a star. Actually, you don't see the star. The star is in the center where you have the yellow star actually, and a black point. And this is to actually remove the light from the star, because otherwise we will not see the planets. And then you may see that there are 4 points that rotate around the planet. And you can see also the dates that range from 2009 to 2015. And then if you look, for example, at the planet that is closest to the star, you would see that it rotates around 6 years by approximately, I would say, 1/3 of a quarter, so 1/12 of a total circle. So it means that it will take 6 times 12, so 72 years to do a round trip around the star. And that's interesting. This confirms what we know in the solar system, because if you look at the size, this planet is around 20 astronomical units from the star. And this is also typically the distance between the star and Uranus in the solar system. And Uranus has an orbital period of 84 years, so which is similar to what we just found just looking at these images. So when you look at this kind of images, and you need many of them to know how fast the planet is rotating, then you can confirm that this is really a planet. Now, I will do a little quiz. So, and I will ask you to answer in the chat to 2 questions. The first one is, do you know what is the movement of the sun that is due to the rotation of the Earth? So just write in the chat if you think, I mean, how big the sun moves from left to right because the Earth is rotating. And second question, do you know how many exoplanets or extrasolar planets we know today? So I will now show a movie where I don't show the answer. This is a movie that was made by NASA, and this shows, I will start it, this shows the galaxy, and then each point that will appear are planets that have been discovered, and then you have the years. So you see first planets in the 90s, and then you have around 2000, you start to have more planets. It's a very small number actually. Very small number. And white and small planets. So you see that from 2014 there is a total of 9. Okay. So yeah, what I was saying is that you may have seen them in 2014 and I think 16, I guess. there was an increase in the number of planets that were known, and you can see here on the left there is kind of a cross, which is not the Swiss cross, but this is what the Kepler satellite observed, that you have many planets that were discovered at this location. So now the question is how many planets and what is the size of the radial velocity? Sara, what are the answers?
So let's say Oleg did a nice suggestion of putting it into apparatus, and apparatus said like in 2024 there's 5,030, and he did a very good estimate afterwards saying like there would be another 10%, so more like 6,000. Dion just posted like the NASA page saying which is 6,000. That does not count, Dion. And yeah, that would be the answers we have so far.
Yeah, so we have more than 6,000 extrasolar planets that are known as of today, which is quite big, I would say. And you see them actually here on this map. Now, regarding the first question about the effect of the Earth on the Sun, I don't know if somebody tried to answer that, if Albertus tried to answer that.
Oleg is asking to repeat the question.
So the question was, so you have the Sun and you have the Earth that rotates around. And this makes the Sun move a little bit. And what I ask you is, what is the extent of this movement? Does the Sun move by 1 billion kilometers, 1 micrometers? I mean, just to have an idea.
Let's say that Jupiter is also going to contribute to this motion, but we are just isolating the Earth for now. So the Earth does cause some kind of effect on the Sun in terms of motion, and you need to guess the order of magnitude.
Are there answers?
You can say something absurd, we will not bite. Chai says 2 meters. Oleg says a few meters.
Yeah, that's interesting. Actually, the correct answer is 13 centimeters. So it's a bit big. So you have to imagine that because of the Earth, the Sun is moving like that, which is pretty small. If you imagine how big is the Sun, it's super big. So it's 1.5 kilometers in size, the Sun, and it moves by 13 centimeters because of the Earth. Now, the effect of Jupiter is more like 10 meters altogether. That's quite interesting. Okay, so actually what I mentioned is the velocity. So you really have to think that, I mean, I take 1 second to move like that, you know. So this is exactly what is the speed that the Sun is moving at this speed. Of course, because the orbit lasts 1 year, it will move more. But it's really, you have to imagine that the Sun, this 1.5 million kilometers, is moving at this velocity, which is pretty small. Yeah, okay. Okay, so now, the question that we can ask is about, with all these systems, what, I mean, are there systems like the solar system that you can see here? Of course, that's not to scale, with 8 planets. And in particular, do we know if there are planets like the Earth that exist in the galaxy or elsewhere? And this is very interesting because we are living now at a moment where we have the possibility to answer this question from the observational point of view. And this is thanks to big facilities, big telescopes that already exist or will exist in the coming years. For example, on the ground, there will be the extremely large telescope that you see here. On the top, you have a visualization, and just below, you have now how the telescope is. So you see that the dome is starting to take shape. And this will be able to detect this motion of the Earth, of the Sun, because of the Earth around it. You also have James Webb Space Telescope that I guess you have heard about. And then there will be later on the Habitable World Observatory, which is a project for a very big space telescope that will be able to directly take a picture of a planet like the Earth. And last but not least, we have this project that is led by our colleagues at ETH in Zurich, which is a set of 4 telescopes that work in tandem to be able to observe directly a planet like the Earth. So what is very interesting is that we have, or we will have in the coming years, the capacity to find other Earth. But the trick is that we need to know where to search, because it takes a lot of time to observe a planet like the Earth. And so the key is, can we know where to search? Can we know where are planets like the Earth? So for this, there are two possibilities. Either we can just look at random, but then this is very difficult because, as you know, there are many stars, and so the chance to fall and to find by chance on Earth is maybe not so big. Or we can do an optimized search, and so we need to have a way to optimize the search in order for us to say, okay, maybe for this star there is a bigger chance to have a planet like the Earth. And this is where the architecture of planetary system comes into play. So what is the architecture of planetary system? It is the correlation between the properties of planets in the same system. And if we can understand the formation of planetary systems via numerical models, then we may use what we know for some stars. For example, we know that in a star there is one planet that is easy to detect. And this one planet could tell us, okay, maybe there is a big chance that there is an Earth in this system, or maybe there is a small chance that there is an Earth in the same system. And then we can use that in order to understand where to search planets like the Earth. So what we have done in Bern since actually 2001 is that we have developed a very complex numerical model that is able to compute the formation of planetary systems. And practically speaking, for people who are a little bit in mathematics, it means solving a lot of differential equations. So that's an image of our model. So every box here is a set of differential equations, and they all represent some physical phenomena that are important in the formation of planetary systems. So I will not enter into all these details, but what is important to know is that this is extremely computationally expensive. So for example, if we want to simulate the formation of 1,000 planetary systems, with up to 100 planets in the system, that will need for us 1 million CPU hours. So months of computation on a cluster like the one that you see here, which is here and there. And at the end of the day, when we do this computation, we end up with a diagram which is like on the right here, where you have all these points represent planets that have been formed in the model, in the computer, with on the vertical axis the mass, and on the horizontal axis the distance between the planet and the star. And this is a logarithmic scale. So 0 means the mass of the Earth and 1 astronomical unit. 1 would mean 10 times the mass of the Earth and 10 times 10 astronomical units, and so on and so forth. And just to see where in the solar system here, I've depicted here the planets of the solar system, except I forgot one. So this is okay. So let's move to third part, where I will hand over to the architectural planetary system using generative model. And for this, to introduce that, I will take the same diagram, but now I will connect the planets that are orbiting the same star. And then really you have to see planetary system like this kind of line that you see here. So here are the 8 planets, a line in this diagram like this one for the solar system. And now Sara will explain you how we can use AI to model this.
So just out of curiosity, what we are saying here, that's actually these simulations we do in Bern are computationally expensive and everything. This was a challenge we proposed in the Bern Hackathon last week. And we have people trying to get into this challenge and produce these planetary systems easily. And today what we do is like we present our method to solve this issue. So we don't want to use the algorithm that was developed in Bern. We want to take advantage of what it produced in the past to try to replicate more and to increase the number of statistics we have. So starting with these diagrams in which we can link the planets with lines, we can say that this is kind of a sequence. And speaking about sequences, now let's talk about something completely different, and let's go ask apparatus a very important question. So tell me something interesting about exoplanets. And if we ask apparatus to tell us this, it will write this very nice text about habitable planets and life, and everything seems to be the important or interesting topic of the moment for exoplanets. And it does write some very interesting facts, actually. And what is interesting about it is that actually apparatus is able to create a text which makes sense, and it predicts the next word based on the previous word. So when he's constructing these sentences, it takes the first word, he predicted it, and then the second word will be related to the first word somehow. And in a sense, this makes sense for planetary systems if we look at them from the point of view of lines and points that we saw before, because then we can see them as maybe these words in the problem. So even more so, we can see them as characters. So we can put them in the same diagram as we did before, and we can try to associate in this space of mass and semi-major axis a character grid. And we have our planetary system in here, and we want to encode it into something that a large language model, an LLM, can actually understand. So what we start to do is like, let's see, the first planet is quite small, it's close to the star, so it should have a semi-major axis, which is quite small, and it is still quite small in terms of mass, so it should have a character which corresponds to this first E, their signals. Then the second planet is a little bit bigger in mass, so it will be a little bit above, and it will be farther away from the star, so it will correspond to a B. The third one, and so on, and then you can create a word. So this planetary system composed of 4 planets would be called a brie, because we like French in here. And we can do this for all the things that we simulated in the past to try to see if there are correlations between the model, between the data we developed here in Bern. Because if we can find these correlations and we can understand that, for example, tiny planets, they tend to be closer to the star while giants are outside, or that, for example, it's not possible to have multiple giant planets in the system, then it would be easier to try to create planetary systems from scratch and to try to use these new statistics to understand how to guide these observations in the future. That being said, so you kind of like start with these planetary systems here in Bern, and you convert them into words. So here are 3 examples of 2 words, completely random with the grids. So we did this for 25,000 planetary systems that we managed to compute in advance. So these ones, they have up to 20 planet embryos, like you saw in the beginning, that embryos could be potential future planets. Doesn't mean that they are future planets. So, but because we start with 20, we know that our words should have at most 20 characters. And we give these 25,000 words to an LLM, and then it will try to predict, try to see the relation between the different characters. So it will start with the first one that we see here in the first row, first column. We have the probability of E being the biggest one, so it will pick this one. And then once you have picked this one, maybe the O in the bottom is actually the most probable one with 7%, so it will pick this one. And then you go like this, so forwards, so on, and then you start to the end of like it trains, it understands the characteristics of these words, and in the end it will produce new ones. So what you need to do is like you have this new possibility of producing a lot of new words. You just need to convert them back to what they were in the past using the grid we saw before, in which we used in the beginning to convert planets into characters. So you do the inverse process, and you manage to actually create planetary systems. So this is what we did, and let's do a pop quiz. So we did this, and we compared with things we produced here in Bern but did not use AI, and we produced also AI-generated ones. So in the picture here in the right, you have some which are produced by AI and some which are not. Do you know which ones are which? Can you tell in the comments which ones do you think are which? We have answers.
Not yet.
There should be a few of them which are easier.
So do you see a difference statistically between 2 groups of these planetary systems?
And no, not all of them are generated by AI. We had this question before.
Half are from AI and the other half are real ones. There are ones with a more pronounced slope. Yeah.
More pronounced slope. Could you just say a little bit the row or the column, just to give us an intuition?
More sparse, homogeneous data equals synthetic. Yeah, interesting. Row 3, column 5.
Row 3, column 5.
And then Dion says row 3, column 3. Yes, it is a very strange one, actually, to this one. Yes.
Yes.
So, yeah, this is pretty good, actually.
Yeah, not that bad.
Yes. Okay.
Any more final thoughts? Now it's the time. Well, for the people who said row 3, a tree, that's good. Row 5, tree, that's good as well. Actually, the ones which are encompassed by orange, they were the ones generated by AI. And we assume you would fail, so that's why we're putting this in here. But actually, you're better than machine classifiers. Well, in the end, we actually, to be sure, because these are a few of them which are emblematic, which we put it in here to show. But it's not a very trivial task. So what we did is we actually trained some machine learning classifiers. We fed them 50% of fake data and real data, and we allowed them to understand through training at what point would they not be able to distinguish both. So that's what you see here, is that in the beginning, because the transformer model or the LLM did not understand yet how the correlations are between the planetary systems, it creates bullshit. And this is something which is quite easily distinguishable, except that when you start training enough the large language model, it will start pick up on the correlation. It's like when you're constructing a sentence, you know that you need to start with some kind of subject and then you put a verb. This is more or less what it learns at some point, is that it needs to do this for certain character structures. And then you reach the end and you cannot really distinguish that well what is real and what is not. So we did this and we convinced ourselves that this was good, but to really put this to test is like we go for an example, because what we want to do is to use this to actually guide the future missions and future telescopes. And we start with a very nice example. So in 2019, there was this mission called TESS. It is by NASA. And what they did was they observed some stars and they used the transit method, as Yann explained, to try to see if they could spot this kind of like shadows in the star that could be done by planets. And they went around this very nice star called Thor 469, because we are not very creative as astrophysicists. And they discovered the planets. They discovered something which is a little bit smaller than Neptune. So they called it a sub-Neptune, and it has the name of the star plus a B corresponding to the first planet being discovered. So this planet was actually very close to the star. It has a period, so it goes around the star in 14 days. And it's a little bit more massive than our Earth, so 9 times more massive than our Earth. And they discovered this, and they did not know what the system was yet to give them. So they were happy, and they decided like, oh, maybe we can come back in the future to have a little bit more measurements and to be able to, characterize better these planets. And if they had asked us at the time, well, is there something else there? If we used only our model here in Bern, then we would not be able to say anything. Actually, we use a high resolution model, which means in the beginning, we put inside 100 planets embryos and we let them evolve. And in the end, we will have something up to 28 planets in this data set. We would find 3 planetary systems which somehow have something close to this planet, but it does not give you enough information on where it would be and what kind of mass it would have. And if we use the other simulations, which we actually use to train our large language model, in the end, we would have a little bit more statistics, meaning 17 systems. You could start to see something if you wanted to, especially on the mass, but you see that the uncertainties, which are these bars on top of the darker bars, it's very big. So in the end, you might have just had luck with the kind of clustering of the darker bars. So you wouldn't be able to say anything. Turns out that if you use our model, the AI generated model, now you start to see features which are a little bit more pronounced. And let's look at the first graph on the left. It says distribution of observable planets, things we can see with the current missions that we have. And there's a peak between 2, 3, and 4, which means that, well, TESS discovered 1, but maybe there's more than that. And you start seeing that in the mass, we have something which is at 1, which Yann said that corresponds to around 10 Earth masses. And we have a few peaks. We have 2, I would say, main pronounced peaks in the semi-major axis, one being at more or less -1 and another one being at 0. So there should be something else there. Turns out they came later to be able to identify better the B planets, and they discovered two of them, the C and D. C and D being closer to the star, and if you actually look at the mass, you have 4.5 Earth masses, 5 Earth masses, very close to the star, 4 days and 6 days to actually do a turn around the star. But where do they lie in our plots? Actually, they lie more or less in the regions that we predicted in the beginning. And if you see the first one, which is the joint distribution of the mass and semi-major axis, they're right in the middle of the concentrated area where there's more probability to have planets. While for the mass, they lie slightly below the peak, but this is not very dramatic. Actually, it is a good estimate that the peak should be around 10 AU, 10 Earth masses. And for the distance to the star, in the end, they lie in one of the peaks. So in the end, maybe if Tess had consulted it at the time, we would have been able to say something. So that being said, this is actually quite relevant, just to give a little bit more emphasis again, because now we have Cheops, which is a very known Swiss mission. We have James Webb, also quite known by NASA in space. But what is the big news is that there's going to be a mission led by ESA and also with a lot of involvement of Switzerland in space next year, which is Plato, at the end of the year, if everything looks good in the planning. And this mission is going to be going there to actually look for terrestrial planets. So if our algorithm actually works correctly and we assume that the data we have to train it is actually quite good, this would be a very good chance to actually use something to guide the observation and not do the blind search that Yann said in the beginning. And later on, there's even going to be Ariel, which is going to be able to give more intuitions about the compositions of these planets. So it would be really, really nice to have some kind of intuition to know where to look for. And we hope that with our algorithm, we can do that. And that would be it for the use of AI. And we are now open to your questions. So if you have questions, please put them in the chats and we will try to answer them.
So there was a remark from last week in the chat who was working on the challenge. And you can see it here. Yes. So do you have questions on whatever we discussed?
Or do you have just curiosity questions that we can answer?
Not on black holes, please.
Well, if you're on black holes, it might be funny. And thank you for the feedback. The interface was actually quite nice that you did on the Burn Hackathon.
So there's a question from Oleg. Do you expect experiments of the Mars mission to help exoplanet research? I can start.
Yeah, sure.
So I think it's a very good question. In general, you have to consider that the solar system should be like any exoplanetary system, but we have a chance that we live in it, so we can study it in a lot of details. And everything that you learn on the solar system, you have to include it when you try to understand exoplanets. And Mars actually is something that is very interesting because, I mean, if you look at the mass of Mars, it's 10 times smaller than the mass of the Earth. And this is something that is actually very puzzling because in every formation model of the solar system, any traditional model, you would expect that Mars and the Earth have kind of the same mass, like Venus and the Earth. And this is not the case. And this was, for a very, very long time, a very strong puzzle. And then this puzzle was solved by different kind of models. And these models, for example, they were always showing that there was some movement of planets in the solar system. So somehow the fact that Mars is so small was an evidence that there was some movement of planets during their formation, which is something that is also the case for exoplanets. Now, in terms of the Mars mission and the Mars sample return, for example, I would say they can have two kinds of influence. First, they can tell us what is exactly the isotopic composition of rocks on Mars, and this can tell us actually from where comes the material that end up in Mars. So that's something that is very important in the general context of exoplanet formation. on a different point of view in terms of the search for life, this is clearly something that is extremely important because my own personal bet, but this is mainly only me, is that if there is a place where you can find life not on Earth easily, I would say, this is probably Mars. I'm not saying that there is necessarily life on Mars, but frankly, this is the easiest way you can try to look at. Exoplanets are very, very far away. There will be always some ambiguity if you see some sign of life. But in Mars, if you take the rock back to Earth and then you see that there is something that could be interpreted as life, then this is a very, very direct and solid evidence. And the only other place in the solar system where we think there could be some life is on Europa, a satellite of Jupiter. But you see, that's super, super far. And so sending a probe on Jupiter, on Europa, bringing back some material, I think, unfortunately, none of us will see that because that will take 1 century. So Mars is super important, I would say, in this kind of research for life. I don't know if you want to add something.
Well, I have 2 or 3 comments to add. I think like what we need to be careful though with the solar system and Mars in particular is that we don't want to have a very tunneling effect when we are doing our research. We need to be as open as we can. So it would be nice to learn something from Mars. And if we do, it would be also nice to have a bit more intuition to what we are looking for, but we should not take this as the only possible solution. And on top of it, I wanted just to add something about the life in the solar system. There are actually teams in the USA mostly suggesting that planets like Venus could actually host life in a very different way than that we are expecting, while Mars and Europa would be in a more similar way that we are expecting, more in terms of bacterial kind of life, at least. Yeah, so I would say, Oleg, definitely Mars experiments will tell us more information. We just need to be careful with what kind of information we are learning from it.
So we have a question from Michael. How much easier is it to analyze the atmosphere or chemical composition of an exoplanet based on whether it is at 20 or 200 light years away? So actually, the distance is not the key, but the luminosity, the number of photons that you receive is the key. And of course, this is related. If you compare 200 light years to 20 light years, that's 10 times further away. So there is 100 times less photons. And so it means that it's 100 times more difficult. Not because it's far, but because you just receive less light. And that's what makes this difference. This is actually one reason why many missions now try to find exoplanets as close as possible to Earth. Because if you want to study the atmosphere, then it's better if they are not so far.
Mm-hmm.
I don't know if you want to add something.
I think that was exactly what I wanted to say. So there's a question about do you use a model to check the habitability of found exoplanets in our research system? We are not yet at that stage because on top of it, I mean, to define habitability is quite complicated. Like Yann in the beginning, he was mentioning Mars and Europa, and there's this team in the USA saying that Venus could also have it, but we don't know necessarily what life is, or we don't have a concrete definition, and we do not have the parameters to actually narrow it down. We can base on what we know in the solar system, and what we usually do when we search is we start looking for water, because that's what we know, that's in Earth, life's generated on water. But the team in USA, they are arguing that it can be in dilute, for example, either chloric acid, is it sulfuric acid or something? One of the two. I mean, they claim that this could be also another place in which life could arise. And if that's the case, then we should look for this kind of components in the atmospheres. So it would be quite difficult to say like what is habitable or not.
So a question from Dion, given that we currently cannot travel or inhabit exoplanets, what motivates scientists to search for Earth-like planets? Is it curiosity, the pursuit of discovery, the desire to understand planetary systems, or something else? I would say it's probably a mixture of different things. I think if you take the big picture, I would say, okay, we always want to know to what extent we are unique, right? So there was this question, to what extent is the Earth unique? I mean, are there other planets? Yes, we know where they are. Now the next question is in terms of life. I mean, is there life elsewhere in the universe? And also, what is how easy is it for life to form? At this point, we only have one example. And before you can try to find life, you need to try to find a place where maybe it could be. And this maybe it could be is then related to what we call Earth-like planets. So Earth-like planets, why? Because we know for some reasons that life could not really be in Jupiter, okay, just because temperature is too high, pressure is too high, okay, you cannot have life there. So we kind of know that if a good place to have life, and we know for good reason, is a planet that is similar to the Earth. So trying to find the Earth is the first step to then maybe trying to find life. And then the second reason is we try to find Earth, but all kind of planets, because this is a way to help us understand how planetary system forms, like the solar system, and again, to what extent we are unique or not. I don't know if you want to add something, Sara.
I would say also, I mean, we are curious, so the curiosity point is actually quite important. We want to know where we originated, where did we came from, and if there's like some fundamental physical laws that rule this all, and it's kind of like curiosity which drives us also in a way. I mean, I'm a curious person, I mean.
Yeah.
So, yeah. So there's also another question. Do you see other areas in research that could benefit of a similar approach?
Yeah, I would say what we do here, actually the trick in what we showed was to consider this, sequence of this planetary system as sequence. But there are many things actually that you can consider as sequence, and it has, for example, transformer, they can be used to model DNA sequence, or they can be used to model maybe, if you do a clinical research and then you want to follow, you follow by blood test or whatever, how they evolve, and you want to predict if they will be, if they will die by this disease or probably not. And this is sequence modeling. And I would say transformers are very good at sequence modeling. So every time you have a sequence, could be a time sequence, could be a space sequence, as we have done, then you can use something that is similar. And this is actually used already in some research project that I know of.
Yeah, and biology is really one of the strong ones that they are using this to actually generate vaccines and cures to some problem.
Which actually brings us to the remark of Oleg, which is actually very interesting. The Swiss AI initiative also has a project on foundation models for modeling the complexity of life and molecules. Yes, this is actually, this is very interesting. We know that AI is very good at modeling complex interrelation between many actors. Actually, actors could be genes, could be molecules, could be whatever. And so this is something that is super interesting to model. And this is also related to what Sara mentioned before. When we search for life, for example, we have in mind, okay, a life which is, like trees or people like us, but maybe there is a completely different pathway that would form something that would also be called life, which is maybe very different from us. And it is extremely important to try to understand that for two reasons. The first one is that if we find a life that is not based on DNA and carbon, I would say, and water, in particular in the solar system, then that would be super interesting, because that would prove that this is an independent starting of life. So you don't really imagine that you have a common starting between a life based on carbon and the life that will live in Venus, for example. So that will mean that producing life is something that happens frequently, at least if you have two cases. So that's the first. And the second thing is that, of course, if you want to search for something, you have to know what to search for. And now we search for things that are more or less always related to life as we know it. So if we can extend the parameter space of what we search as a result of this complex chemistry model, that would be super interesting.
Well, I like Chaifan's question. When we have AI super intelligence, we will be able to better find extraterrestrial life with yet unknown approaches. I would say that, I don't know. You need to ask the AI superintelligence model, but I would say that we keep on mentioning this, we are very looking for life as we know in the context that we are and with the environment that we have. And AI maybe will look at it in a very different way because it's not reasoning in the same kind of way as us. So maybe they will find something which is completely different in our approaches, and it would be quite nice to see what they come up to. Maybe they will not find anything because then you need actually more context or something, or they are actually created and they are not life by themselves. So I don't know, but it will be fun to know what they do.
So I think there is something also interesting here. So when you speak about AI, AGI, superintelligence, whatever, so any AI cannot be stronger than the laws of physics, I would say. So when you mention extraterrestrial life, so I don't know what you have in mind, but for me it's like, intelligent life. And then there is something that is very important, that's the light of the speed light, right? And so whatever AGI, it cannot detect any message that comes from very far, except if it was there a long time ago. And I think something that is interesting for us to remember, if you look at the galaxy, and if you look at the radio emission that we have been doing since the beginning of industrial times, then this is very, very, very small. And we have not traveled until only 10% until the center of the galaxy. So that will take 25,000 years until our pollution by radio or TV emissions travel until the center of the galaxy, and another 50,000 years until it goes until the end of the galaxy. So this takes a lot of time. And so now if you speak about extraterrestrial life, so little green people, then if you want to detect them, they have to be there on a very, very long time, because otherwise you don't have time to receive their signals. So that's something that any AGI cannot go beyond. That's the laws of physics.
Well, just a remark on that. The Chai says that maybe wormholes to shorten the distance you need to travel might work for that case.
Yeah, but then it goes to black holes, so I'm not coming to that. But maybe that's something I wanted to add. Maybe the laws of physics that we have in mind are not the correct one, and maybe an AGI could find other laws of physics. And maybe, okay, everything then has to be rediscussed.
Okay.
So, yeah.
Question of Dion, are you familiar with AI models like AlphaFold to predict protein structures from amino acid sequences? And if so, do you see your planetary system models as being similar or different from that approach?
Yeah, so I know a little bit AlphaFold 1, not 2, because I'm not sure if the 2 is public, but I know it uses transformers. I would say there are two differences, or three, I would say. First is that the amount of data that they have is huge compared to ours.
Yeah.
There are many, and the second that is the funding that they have is huge compared to ours. So please donate. And the third one is that it is not only based, at least the AlphaFold 1 is, so AlphaFold, what it tries to do is you take a sequence of DNA and try to predict the shape of a protein, and which is super important for many things like drug discovery. Yeah. And they are, so they model sequence, but then they also have in their training a lot of other information that have been gathered from different experiments. So they put all this data together. It's not only the sequence, there is more information. So, but at the core of AlphaFold 2 now, which also got the Nobel Prize, actually, is a transformer architecture, which is sequence modeling again. So, you want to add something?
No, I think you said it all for AlphaFold. Is there any more last minute questions? We still have a bit of time. Thank you for your comments. Yes.
Yeah.
And thank you for organizing that hackathon. It was really, really cool. So as its theme of Swiss AI says, like, this is our session, it's coming to an end, but there are more interesting on-air sessions that you should check out on the website.
Wonderful. Thank you so much, Yann and Sara, for this super interesting AI on air. And yeah, you see other sessions, please rate us, and you can rewatch that and other sessions on YouTube. Thank you so much.
Thank you.
Thank you for hosting us.
Bye.